Next chairman is Sandrine, if I'm right. So Sandrine, if you want to take...
I will take
the floor.
I will take it from here. So yeah, it's my. I'm really happy to chair this session on surgical skill analysis, and I think it's a really good example of a transversal work that has been done in the LabX, because I think it concerned almost all, if not all, the labs involved in the LabX. And our speakers for this surgical skill analysis talk will be Marie-Aude Vitrani, who is a university lecturer at Sorbonne University in the ESIR lab and the AGAT team, and she develops robotic systems to improve the user's perception and gestures, involved in surgical procedure and gesture analysis, conception and robot control for surgical gesture assistance, and experimental and clinical validation. And she is also, among other projects, the head of the CAMI integrated project, the surgical cockpit. And our second speaker will be Pierre Jannin, who is INSERM senior researcher at the LTSI laboratory in Rennes, and is the head of the Medicis team. And so he has a very long experience in the design and development of CAMI surgery systems, and he has a particular interest in surgical data science, in particular the modeling and of surgical procedures, the study of surgical expertise, and surgical training and validation methodologies. And just a kind reminder before we start, for those who were not there early in the morning, if you have questions, please use the chats, whether you are on Zoom or on YouTube. Thank you, Marie-Aude and Pierre.
Thank you, Sandrine. So, as Sandrine said, I am a roboticist, and you may wonder why I am interested in the analysis of surgical skills. And I would say that my main motivation is probably the same one that has driven CAMI researcher for 30 years. Namely, it's to help surgeons performing better surgery. And our hypothesis, by doing surgical skill analysis, is that with a better understanding of what is a good surgery, what is an expert surgeon, or what is an efficient team, might lead to more relevant assistance. And it could help us in designing more efficient system and more efficient robotic system to assist both practice of practicing surgery or training for surgery. And the practice of surgery is often seen by us engineers as a problem of dexterity, and it is assumed that gestural or perceptual gestural assistance will improve surgery and might be sufficient. But of course, performing a surgical gesture implies mobilizing many other skills than dexterity alone. And I would ask, is it useful to improve dexterity if the problem is a lack of anatomical knowledge? If one does not know what is the next step in the procedure? If you are not aware of the teamwork and so on. So moreover, when you practice a gesture, this gesture is not always good or bad in itself. It is good, it might be good in a given situation and bad in another situation. So clearly, we cannot reduce the practice of surgery to gesture performance alone. And technical that are here, or non-technical skills should be taken into account. And even more complicated, one must be able to understand the interrelationship between all these skills, and this might be the dream goal of the researcher trying to model and analyze the surgery.
To to summarize, to sum up the different skills which are involved, they are, as Marie-Aude said, they are covering both technical and non-technical, from dexterity to interpersonal skills. And what we want to present to you today is how and what can be done to analyze these different type of skills, and how we can do that, and why it may be important to do that. So we will show you some examples, mostly on the technical skills, because we don't have time to cover everything, but to show you how data-driven approaches may help to understand these different skills. And for that, we will start with dexterity, of course, because this is obviously what is the easiest things to do. So why it is easy? Because nowadays we are able to have access to motion data, to different data that allow us to study this surgical skills. So for example, what you see in this video is kinematic data that is acquired through a robotic system. What we will present also today is all the work that has been done within the CAMI LabX and by the different PhD students funded by the PhD, the CAMI LabX. But not only, we will also include some other example to show you what can be done. And for example, this example is how we can collect data from kinematic data from the system. So I say we can collect data from robotic systems, but we can also collect data from simulators. And the interest of collecting data from simulators is to also study the surgical skills, but in a simulated environment, which is easier to control. And if you go through a simulator, if you practice surgery through a simulator, you are using a computer mainly, not only, but most of the simulators available nowadays are based on a computer, and then you can collect this kinematic data, and you can analyze this kinematic data with different approaches. This one is more a supervised statistical approach, where you compute features on the kinematic data, and on these features you compare if there are differences between different level of expertise, between different participants, between different users, and you can show that some features computed on the kinematic data clearly highlight statistically significant differences between population of surgeons. So you can do it with simple statistics. You can also or unsupervised analysis that also will outline how this kinematic data are representative of the dexterity, of the technical skills of the different populations of surgeons. Then what you can do is to try to go a bit further in the analysis of this kinematic data. And for example, a work we have done with Montpellier was to, if we can, by machine learning, do some compute directly the relationships between the metrics computed on the kinematic data and more usual and standardized scores that are used to quantify or qualify surgical expertise, such as OSATs. And what we demonstrated in the preliminary work is that, yes, machine learning is able to predict some of this value of the OSATs scoring system just by relying on kinematic data and on metrics computed on these features. Another work that we did with Montpellier, with the LIRM laboratory in Montpellier, joint PhD funded by CAMI, was to compute if we can also work on the user interface, so work also on different and study how the impact of user interface, for example, to drive a robotic system by a contactless system, and see what could be the impact of this new interface on the kinematic data, And what we showed at this time by analyzing the available data is that finally this kind of new interface to drive or to control a robot has a behavior which is very similar to more, I would say, expensive interfaces.
So at EasyR2, we were interested in the trajectory of the instrument that we can compute directly from the motion of the end effector of our robot. And the first question we addressed was how to assess the performance of the assistive system. And before being able to guide a gesture, we wanted to be sure that we were applying the desired effort, the desired guidance, and we start working on evaluation of the transparency of our device, which is the capacity to not disturb the gesture. And this was our first work onto dexterity. And then when we show that the robot was transparent enough to not disturb the gesture, we try to show that there are an impact of the guidance onto the gesture, and we analyze all these data with robotic metrics such as precision or speed or time to reach a target and so on. But when we were implementing this guidance system, consideration was given to whether there is a longer-term effect on the surgeon performance. In fact, our system integrates the operating room without major changes to the procedures or to the gesture the surgeon has to perform. And we wanted to know if it was an advantage beyond facilitating adoption, if there is really a transfer of skill, or if there are a particular impact on the dexterity. And namely, the question was, if you practice with Da Vinci robot, do you still know how to operate without a robot? Are you better than you were before? So did you improve your skills? And what was more of importance for us, what's happened if you use our co-manipulated devices? And this question was, does learning task with a co-manipulated robotic assistance result in development of skills when you don't have any more the robotic assistance? And that the main topic addressed by Eleonore in his PhD. So she proposed an experimental protocol in which she brought naive subjects and residents, and the participants were divided into two groups, one training without robots, one training with robots, and they participated in 3 sessions, a long learning session and 2 short pre-learning and post-learning sessions. They perform standard exercise. During the long session, they perform peg transfer exercise. During the short session, they perform peg transfer exercise. And during the learning session, loops and wire and pee on a peg exercise, which are classical training exercise. And the main goal of this experiment is to study whether learning through learning classical laparoscopic surgery can be done through the practice of a related activity, namely a co-manipulated activity. A second objective we had was we wonder whether co-manipulation gives better performance compared with classical minimally invasive surgery, which was the second objective. And if we look at the results for resident participants, we observed that both groups took the same time to perform the final exercise after the learning session, though it suggested that they have equivalently improved their skill, whether they were training through laparoscopic surgery classical or with co-manipulation assistance. And regarding our second objective, we observed that co-manipulation improves the performance for some exercise, but not for all the exercise. Namely, we observe better performance when the subject needs fine motor skills or when the task was a precision task. But when he had to mobilize proprioceptive or complex manipulating skills, like for performing loops and wire, we do not observe improve in the learning process. And that seems to mean that the other skill than dexterity should be training in parallel if you really want to learn surgery. And these results are very similar to those of Ninon, who was another PhD student in CAMI. And in her thesis, she proposed specific sessions to improve both dexterity and visual perception. So the subjects were trained during 5 different sessions, and the difficulties are divided to propose a progressive training, first onto the manipulation with one hand, then to the coaxial view, to the off-axis view, manipulating through fulcrum effect, etc., until you can reach the full training session. And in parallel, she had a group of students that performed the 6th session, but with only the last task. And what she observed is that the performance achieved after this session was better for the group that were trained through this progressive session than for the group that only had the possibility of training onto the complete task. So to conclude on this work, I think that they are too far from ground truth. And we cannot conclude that the same behavior will occur during a real surgery. It is not sufficient to know how this observation can help residents in medicine concretely. So obviously improving dexterity is important, but the context seems to be essential for training and for learning. So we have to face the difficulty to implement more realistic protocols involving all the other skills, such as the knowledge of anatomical structures, the way to use the instrument, and some other questions that are not only how to manipulate the instrument.
What has been demonstrated in the literature is that this dexterity or skills related to manipulation only account on about 25% on the success of surgery, on the quality of the global quality of surgery, and that the 75 remaining percent are based on the other kind of skills. So these are very important to study also. So the second type of surgical skills we would like to discuss with you are related to the procedural skills. The procedural skills, as it was briefly mentioned by Professor Wiber at the previous presentation, they are considered like recipes. So the way that the scenario you follow to perform a surgery. So the procedural knowledge is a bit between the technical and the non-technical skills. Of course, there is no perfect frontier between both. and the way that it has been addressed this last, let's say, 20 years, rely on a hierarchical decomposition of this procedural dimension, and it's what we call the granularity levels of surgery. So if you start from the top, a procedure may be broken down into phases, each phase into steps, each step into actions, each action into smaller atoms, and finally, if you go really deeper, you can reach the kinematic, the gesture itself, represented by kinematic data. The way that the procedural knowledge has been addressed rely on a semantic description of these different levels, except of course the very lowest one. And for example, the activity level is usually described. One activity is usually described as a verb that represents the action performing the activity, the instrument which is used to perform the action, the anatomical structure on which the action is performed, the time, the start and end time, and sometimes who is performing this action. So you have an example below. In order to ensure a rigorous representation and modeling of this procedural knowledge, what we proposed was to rely on an ontology. And an ontology is a very formal representation of semantic data, which consists in describing the main components of a universe, the relationships between the different components, the attributes related to each component, and some logical rules that manage this world or this universe of discourse, as it was sometimes mentioned. So we propose such an ontology for surgery in order to describe the surgical procedure. And the idea is really to have a standardized language to describe this procedural knowledge. So once you have that, you can start work on the surgical procedure or the surgical workflow, as it is called sometimes, and use it to assist surgery. So use it in a CAMI systems or CAMI solutions. And one of the important components is to be able to automatically recognize these different activities thanks to sensors which are available in the OR. So I don't want to spend too much time on that. We at LTSC did a lot of work on that direction, maybe relying on computer vision, but not only. So computer vision, machine learning, and recently deep learning, in order to automatically recognize phases, steps, or activity with digital videos, as you can see here. There was also a lot of work in other CAMI. Sorry for that. I lost my. Sorry, I lost my mouse and my screen. Here we are. And there are also other works performed within the CAMI LabX in other CAMI labs, like by Nicolas Padua in Strasbourg, or Gwenole Kelec in Brest, that also work in that direction to automatically, by using computer vision and machine learning, automatically recognize what happened in the videos, for example, that are available. A work we have done with the PhD of Olga Dergashiova, funded by CAMI also, was to try to understand what are the challenges around the surgical workflow or surgical activity recognition. And we addressed different aspects. Of course, we implemented a baseline approach for surgical phase and surgical activity recognition. But what was more interested is we tried to to address some difficulties which are related to surgical workflow recognition, automatic recognition, is a lack of data. It is well known that in surgery there is no, and I will come back to that, and we try to study how we can develop some knowledge transfer, what we call transfer learning strategies in our context. And the first approach that we studied was to see if we were able to use data from the literature, which is a lot available in medicine, to pre-train our networks, to help so to do a transfer learning from text analysis to surgical workflow recognition. So when you see the amount of the data which is available in other image recognition tasks, you can see that they are dealing with millions, billions of data. Where in surgery, and thanks to a review of the literature, we are more dealing with 20, 30, and less than hundreds of data. So we cannot complete exactly. So we need to study transfer learning or weakly supervised or non-supervised approaches to cope with this strategy. So what we studied with Olga was how we can pre-train the networks by doing some analysis of PDF documents, and we downloaded 100,000 of PDF documents related to surgical procedures, and we computed word embedding on that, and we use this to pre-train our networks. And we say it was preliminary work, but we showed and demonstrated that we had an improvement by almost 20%, more than 20% of the accuracy in the activity recognition. Another study that we performed was to study how we can transfer. So is it mean transfer data from any type of surgeries to help our issue, which is to do a surgical workflow recognition? So is it meaningful to transfer data when the levels of expertise are different, when the surgical procedures are not exactly the same, and or when the surgeries are performed between different clinical sites? Can we transfer data? Can we do these strategies of transfer learning if the data are not exactly the same? So we did different study on that, and we demonstrated, again, it was preliminary work, but we demonstrated that if you put all the data together from different level of expertise, different type of surgeries and different clinical sites, we don't increase the performance of surgical workflow recognition. So that means that we need to have adapted strategies in this knowledge transfer or transfer learning. For example, if we put data together within the same surgical procedures, but between surgical sites, yes, we improve the accuracy of surgical workflow recognition. If we pre-train networks by novices, surgery performed by novices or by intermediates, to better recognize surgeries performed by experts, the performances are getting lower. We can transfer between procedures which are quite similar, and we can transfer from one site to another site. So these are type of transfer learning strategies that we studied. We also studied how we can do automatic recognition, not only from videos but also from kinematic data. And there was a work performance of the PhD thesis of Fabien Despinois, funded by CAMI and co-supervised by Montpellier, and we also demonstrated that it is feasible to do that. Once we have this, the recognition of these procedures, then we can start analyzing the the procedural dimension of surgery. So we can start comparing not the trajectories, but the recipes used by the surgeons. And we showed by developing some metrics, we showed that these recipes are significant of level of expertise, of different level of expertise and different surgical practice between clinical sites. In the context of the PhD thesis of Arnaud Golmé, also funded by CAMI and co-supervised by Team C Lab and ourselves, we studied another approach, which is a pattern mining, pattern discovery, and we studied if it was possible to do it on surgical procedures. So we developed metrics based on the pattern discovery, and we showed also that it's possible to distinguish different level of expertise, different clinical sites, just by relying on this dedicated metrics that is computed and estimated on the procedural aspect. So this was about the more about the effectors, the way that the surgeon is performing. So of course we need to make the links between what the surgeon is doing with the results on the patient, with clinical data. So really to try to correlate the procedural dimension with what Marie-Aude mentioned just previously, the anatomy and the success of surgery.
And to do this, we decided to model surgical knowledge that is involved into two surgeries, which are hysterectomy and cesarean. And our goal was to use the obtained model to define tutorial videos, so pedagogical material. The model is based on a CKC model, which means conception, knowing, and concept. And it is a model of knowledge dedicated to build training resources, but it is not dedicated to surgery. So it consists mainly in identifying the steps, the action that allow to change the world, those that allow to control the situation, and the overall domain of validity of the knowledge you are applying. And the main question we address here in this work was how does modeling of a surgical procedure help to improve the quality of training for future surgeons? So on this slide, you can see what the model looks like. I will not get into all the steps, but you can recognize several steps of the procedure. You can see what is called control action. So this means that you have to see a blue-green appearance of the uterus. You have also some operators that are the action you can do to change the world, like continue dissection. And you have some domain of application, which means you have to continue dissection just in case of bulky uteri, then you have to position the trocar in a particular way. And this model is based also onto knowledge like anatomy. You have to be able to visualize the cervix, onto the instrument and the way you have to use this instrument. It is also based on the knowledge of surgical techniques. And when you are training the resident, then it is necessary to ensure that all this knowledge are well acquired. So we use this model to propose enhanced videos, bringing together immersive videos, 3D videos, and in the center, you have the video. On your right, you have a model-based teaching explanation. On your right, you have a zoom view of the surgical site, you can go faster, go back, ask for more information. All of these are based on the model that we developed based on interview and observation of surgical procedures. And the overall protocols we are performing, because it's not end right now, is involve interns that have never practiced cesarean before the training session, and it consists in 2 sessions. The first one is consists in observing this training tutorial on a PC 2D screen, then onto a virtual headset. And at the end, they have to perform real surgery. And so this is a step we are in. We are waiting for the result during the real surgery to see the real impact, as I mentioned before, and not only on lab results. And these first very preliminary results seems to show that if you were trained with enhanced videos, then the participant who were worse at the beginning of the learning made a lot of progress. And some of them became as good as the better resident. But you see the difference. This is with enhanced videos, and it does not occur with non-enhanced videos, which means that the worst student still the worst student after the training. So this is a nice result, but we need to see what's happened in the operating room, and we are now waiting for the evaluation in the operating room.
What is interesting here is that we are starting to make relationships between different aspects of surgery. So between the procedural aspect, and the conceptual knowledge aspect, and that allows also to go towards application. So one what Marie-Aude was showing, which is about training, surgical training. So we can train procedural knowledge in relationship with the conceptual knowledge, and also with the quality of surgery. So this is another additional dimension that should be added in this landscape, I would say. And these are, I will take just 2 examples that was performed with 2 PhD work. Arthur Deraté and another one with Arnaud Gaulmé, both in co-supervision with LTSC and the team CELAB, and both works was trying to make the relationship between what is done and how it was done. So the first work done by Arthur Deraté recently in a PhD, in a recent PhD funded by CAMI, was to try to see if we can directly make a correlation between what is done, which is measured and estimated with both kinematic data and computer vision-based analysis of the video, and also features and metrics computed on the procedural aspect. And can we do a relationship between these metrics and the quality of exposure of the surgical field, which is we know also an aspect of or a parameter of the success of the final success of surgery. And what Arthur demonstrated, of course, again, these are preliminary works. What Arthur demonstrated is that yes, we can do some relationships. Of course, it was not exactly how we expected. We expected more influence, more impact on the procedural, on the prediction of the quality of the exposure. But we also faced an important limitation of this work, is that, and it is luckily, we don't have a lot of samples to learn our machine learning based approaches. We don't have a lot of samples that include a bad exposure. So that will be an important limitation of machine learning in this clinical application of what we are doing, because we don't have a lot of examples of bad practice, which is, again, luckily. In the second similar work, so performed by Arnaud Golmet in his PhD, again co-supervised with between Rennes and Grenoble, was to try to automatically identify from procedural aspects or predict from the procedural dimension, the procedural information, can we identify possible deviation which may be connected to adverse events in the OR. And that was also outlined by Professor Weber that it is important. So we develop a methodology which is both based on machine learning and the use of HMM, and we show that we can predict, we can recognize some deviations based on procedural knowledge, but also with a limitation. So there are some deviations we can predict easily, but the adverse or the deviations which are unexpected and which may be related to adverse events, the not so good. And again, for the same reason, is that luckily we don't have so much samples. So you can see on the table on the bottom right that only 5% of the samples are including deviations of surgery which may be related to an adverse event. So these are one limitation of this work. So as we said, we showed some examples of how we can analyze the surgical skills. They are more than what we did and what we presented today. We talk about dexterity, about conceptual and procedural knowledge. As we said at the beginning, there is a lot of non-technical skills, cognitive and interpersonal skills, such as teamwork, and we don't have time to address that, and maybe that will be for the next year, next CAMI days or next Surgetica. But we also identify some challenges that we need to address.
Yes, the first challenges may be about how to collect data. We need to have more data, but we need to have data with a high quality, and maybe it would be interesting to find a way to share the data issue from control groups that are involved in all our experiments, and this to provide the community with a better and a larger database that could help everyone to compare and to assess the quality of the system or the model that we developed. And to my opinion, the second challenge is how to propose more ecological experimental condition. We have done several work in lab, and the conclusion is that we cannot conclude on what would happen on the operating room or with real students or in real conditions. So I think we have to work onto the better simulated environment or better access to clinical environment.
Other points is, as you mentioned, probably as you saw, we deal with concepts which are quite subjective. The notion of expertise and the notion of quality of exposure or quality of surgery are quite subjective or are very complex because multi-parametric, and so we have also to deal with these challenges. So at the end, what we want to develop is, as also was explained in the previous talk, we want to work together between what the assistants can offer to the surgeon and the human. They have to work together in an intelligent way and for the objective of improving the patient care. So we have to keep that in mind. Our final goal is really the patient quality of life and the clinical outcome. Thanks for your attention.
Thank you very much, Marie-Aude and Pierre, for this very interesting talk. So I'm just looking at the chats, and I see that there is a question from Jérôme Schwetzig in Isir, who was asking how much motivation had an important impact on surgery learning. And he was wondering if the trainees' involvement or the motivation improved during the training when you introduced robotics, and if you had looked at this aspect.
Eleanor asked the trainees if they were motivated by surgery. They all have to perform a training period onto surgery, but they might not want to continue in it. And she does not observe different results between those who were particularly motivated by surgery and the other. But it can happen. It can happen when they would perform surgery. For the learning session, we do not observe difference between them, and maybe it's also because they all find funny to test a virtual headset. So this maybe was more important to motivate all of them. Maybe Pierre, you have worked on motivation also.
It's clear that it's an important question, and these are part of the possible bias we may face when doing experiments. What we have in mind is to maybe to also use of different sensors that allow also to monitor that. That may be a possibility, and to ensure that motivation is high. But the best to do is to again to say it directly to the trainees. It's not as you are in the OR and try to do it well. Maybe the motivation is more the problem of warranty high motivation is more for the expert than for the trainee. The trainee is more motivated than the expert. When you put an expert in front of a simulator and just to collect data, sometimes there is a lack of motivation.
True. Maybe I have a last question. Maybe if you can have a short answer because we're short on time. I was wondering, so we have these simulators which help us gather data to make analysis, but then we know how hard it is to develop those experiments, and it's hard to conclude anything. Then we have the challenges of data acquisition in the OR. So maybe collectively, where should we put our effort? Should we try as a LabX CAMI to try to collectively have big databases from the hospital partners? We all know how hard it is. What would be the priority collectively as people working in that?
Well, I can start just a short answer. You can do your point. I think yes, that would be good. That would be good. But there is so many ethical issues in doing that, especially for clinical data. Collecting clinical data for research is feasible. Collecting clinical data to make it available online, widely, publicly, freely. I mean, real clinical data, not. I mean, what Nicola did with the surgical videos is a good and a nice first point. But ideally, that would be good to have also all the clinical data related to that. So not only the video, but and this is really an issue. But I'm optimistic. We should be able, and maybe this is something we should discuss all together. Yes.
Yes, I think the LabX is the good place to work on this way to collect data, clinical data, but also protocols for group controls, or what are the good metrics that we could share, etc. But you're right, Pierre. The main question is how to share this data involving human. That's the first question, and we can probably work collectively inside the LabX onto this aspect.
Well, thank you very much, Pierre and Marie-Aude.